Okay, today we are going to graph the other trigonometric functions. And hopefully if you've watched the first video that we did and then maybe this supplemental video that I posted on the bottom of the other website, that gave you a really good idea about how to graph trigonometric functions, specifically sine and cosine. And now we'll go on to graph tangent, cotangent, cosecant, and secant. So we have tangent, cotangent, secant, and cosecant, and then we're going to talk about, so after we learn how to graph all of those, we'll talk about how to graph damped trigonometric functions. Okay, and these are trigonometric functions that are influenced by other functions. So we'll talk about that at the very end. So let's first talk about the graph of tangent. Now tangent, we learned and we alluded to earlier, had lots of points where it was undefined. And I told you those were vertical asymptotes, okay? And you can kind of see the asymptotic action happening here. And we'll have all these vertical asymptotes going on through here, right? And these vertical asymptotes happen, and I'm just kind of sketching them in, at specific intervals, right? And they happen over and over and over. And notice these intervals are very constant as I'm drawing them in, okay? So, the vertical asymptotes actually happen, if you notice, this is pi, or negative pi, 0, positive pi, and halfway in between them, at pi over 2, is our first vertical asymptote. So, this point here is pi over 2. This point here where this other one is happening is negative pi over 2, and then we'll have 3 pi over 2 here, and this one here would be negative 3 pi over 2, okay? So at intervals of pi over, not intervals of pi over 2, but at pi over 2 plus or minus so many pi, right, are where these asymptotes are going to happen. Now, that means that we have limits on our domain. And the limits on our domain are the exact same ones that are limiting, that are where our asymptotes happen. So the vertical asymptotes are also where our domain kind of does not have any numbers at it. But conversely, our range is going to be all real numbers because we go from negative infinity to positive infinity over and over and over. Now we do this twice in 2 pi. So our period is 1 pi. Okay? And if you consider that 0, 0 is the beginning, then we repeat again at pi, we repeat again at 2 pi. So we have 2 periods in one rotation of the unit circle. Okay? So that's how that kind of goes with tangent. Now, we're going to start talking next. Oh, and the other thing to notice about tangent, we said tangent was an odd function. It goes through 0, 0, the parent function does, and you can see that if you looked at quadrant 1 and quadrant 3 and rotate it over quadrant 3, they lay on top of each other. And you say, well, what about all these other repeats? Well, if you do that, actually, the repeats lay on top of each other as well, so do the asymptotes. So it's really an interesting function to have be an odd function, okay? It's an odd function, if you will, okay? But think about that and look at your values, okay? But the important values that you're going to need to know, okay? You need to know where your asymptotes happen. They happen at pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2, right? And they also have x-intercepts. The x-intercepts happen at intervals of pi. So 0 pi, 2 pi, negative 2 pi. Okay, that's where your x-intercepts happen. And then you notice that it goes from negative infinity to positive infinity, kind of in a swoosh fashion, right? Within this one repeat of tangents values. Now let's look at some examples of tangent functions, okay? Now, here is 1/4 tangent of x. Now, if you look at the difference between 1/4 tangent of x and regular tangent of x, I did not graph regular tangent of x, but you can see what it might look like here, right? Okay? And you can see how this graph is kind of smushed vertically. Okay? In fact, it is smushed so that it is 1/4 the height of a normal graph. So, and that's why it is smushed. So your amplitude here is 1/4. Okay? Your nothing else is happening with this, right? So it just makes, instead of kind of having a smooth curve like this, for regular tangent, you're going to have a smushed, almost boxy curve, if you will. Okay, now we've got tangent of x plus pi. You're saying, well, wow, that looks exactly like tangent of regular x, right? We have our x-intercepts happening right where they should. We have our asymptotes happening right where they should. And you know why? Because if I phase shift this over by pi, I get the exact same function. So this is going to be just the graph of tangent of x, because the period is equal to pi. Okay? The period for this one was equal to pi as well. We didn't change that with any numbers in front of x. Okay? So the graph of tangent of x plus pi equals the graph of tangent of x, because they both go on to negative and positive infinity. Okay? So that's just an example of how if you add some numbers to your function, you may end up getting the exact same graph, kind of like coterminal angles. Now let's look at cotangent. Cotangent is slightly different than tangent, okay? And you might think, wow, I should expect to see it just kind of flipped across the x-axis. But that's not quite what happens with cotangent. Cotangent actually has domain limitations as well, but instead of being pi over 2 intervals, these intervals are at intervals of pi. Okay? So I have a vertical asymptote at 0, 0, or at the line x equals 0. I have a vertical asymptote at the line x equals pi. At the line x equals 2 pi, 3 pi, you know, negative 1 pi, we're going to have an asymptote as well. Okay? Now, this means that this function does not pass through 0, 0, but it is still an odd function. So this is one of the few odd functions that does not pass through 0, 0. Now, if I were to take this y-axis and kind of flip it down and around 180 degrees, it would still lie on top of itself here in the third quadrant. So the first quadrant and third quadrant, it would still do that. It's going to take a little imagination for you to see that. I wish I could have actually a graphic that would do that for you, but your brain is going to have to make that graphic itself, I guess. But the range is all real numbers. We can see that really clearly with our y values here. Our period, again, we can see that happening every pi, right? And the vertical asymptotes happen every pi, okay? So that means our x-intercepts, instead of happening like they did with tangent, they're going to happen on the intervals of pi over 2. So they kind of swap. Where the asymptotes were on tangent are now where the x-intercepts are on cotangent. Okay? And where the x-intercepts were on tangent are now the asymptotes of cotangent. So if you can remember that, they're backwards like that. So tangent and cotangent swap values for asymptotes and x-intercepts. Cosecant. Now cosecant, what I've done with cosecant is I've graphed not only y equals cosecant of x, which is the reddish function. I've also graphed in blue y equals sine of x, because I really wanted you to see that what's happening with sine is, imagine that we are really just slicing sine down across the x-axis, okay? And then I've got some, when I have reciprocal functions, because cosecant is a reciprocal of sine, and values that I had zeros at for my sine function, when I take the reciprocal of 0, I get undefined. So now I'm going to have vertical asymptotes at those lines. So my zeros of sine become my vertical asymptotes for cosecant. Very important concept here. So we see those vertical asymptotes happening. Now what you can do is you can see the peaks, and I told you these peaks were very important on sine because they are the same points on cosecant. So these are the few points that they have in common. Okay? So the 5 points that were important for sine were also important for cosecant. The x-intercepts on cosecant become the vertical asymptotes, the x-intercepts on sine become the vertical asymptotes for cosecant. And the peaks and valleys for sine are also the peaks and valleys for cosecant. However, if it was a peak for sine, it's a valley for cosecant. If it was a valley for sine, it's a peak for cosecant. Okay? They're reciprocal functions. We're actually physically taking this part of the graph, flipping it upside down, and kind of smushing it up towards infinity. This part of the graph here gets flipped upside down and gets smushed down towards negative infinity. And we just keep repeating that over and over. This is another one of those graphs that's an odd function. It does not go through the origin. Okay? So, my domain is actually going to be all x's, except because at intervals of pi, I have asymptotes. So all x's except integer values of pi. Okay? So all x not including n pi. And then my range is really weird, okay? Because I don't have anything between -1 and +1, right? Nothing there. But everything else is part of my range, okay? So, if it was part of my range in sine, it's not part of my range in cosecant, with the exception of these points where they both touch, okay? My period is still 2 pi, but I have vertical asymptotes wherever I have domain limitations, okay? So, kind of weird. But those 5 points that were important for sine are the 5 points that are important for cosecant as well. Now let's look at secant, okay? Secant, this is y equals secant of x, and this was y equals cosine of x, okay? And I graphed both again so you could see the exact same thing that happened with sine's reciprocal function happens with cosine's reciprocal function, okay? So I'm going to slice it down the middle here again and kind of split it open, okay? Only my domain limitations, they still happen where my cosine function crossed the x-axis, right? But because of where cosine crosses the x-axis, my asymptotes are going to happen there as well. But cosine crossed the x-axis at intervals of pi over 2 plus or minus so many pi, right? Well, my asymptotes are going to happen at the exact same spot. Okay? So my range, again, just like cosecant, was everything except the stuff from -1 to 1, but it also includes these common points. So from negative infinity to -1, union with 1 to positive infinity is my range. My period is still 2 pi, okay? It takes 2 of these cycles to completely finish this off, okay? And my vertical asymptotes happen where my domain drops out as well, okay?
So that's what secant is going to look like for us.
So let's do some transformations of these functions. Let's see what we've got going on here. We've got an amplitude change, right? Is 2, right? Which means instead of it being a nice U-shaped function, it's going to be very sharply U-shaped, right? Twice as sharply U-shaped. We've got some period change. And remember that was 2 pi over b. Our b in this case is 2, so we're going to have our period is going to be every pi for this function. And we've got some phase shift going on. And that's going to move pi to the right. Okay, so when we move a secant function, which is the reciprocal of cosine pi to the right, it's going to start to look a little bit weirder, right? It's not quite looking like a cosine or like a sine function, okay? But it's, if we didn't have this period change, it would, okay? If we did not have this period change and we just moved secant pi to the right, it would look exactly like cosecant, okay? But we have the period change as well, so that prevents it from looking exactly like cosecant. So this means for us, with a period of every pi instead of every 2 pi, that means that we're going to have 2 repeats in a 2 pi rotation of the unit circle, okay? So it means that our asymptotes are going to change location. It means that our peaks and valleys are going to change locations as well, okay? Same with that phase shift. That's going to kind of impact things too. Now this is kind of a little bit more complex type version of things, and again,
You are going to have to learn how to graph this. We'll go over more about how to work these when we get into class, but they'll proceed much like sine and cosine did. Now let's talk about cotangent. We see with this cotangent, my amplitude is 3. Okay, so it's going to be stretched a lot more than the normal tangent function. You can see it's, more like a straight line than anything else. And then we want to talk about our period. Now, a normal period of cotangent is every pi. So we're going to take pi and divide that by pi over 2 to calculate our new period. And so that is going to end up being just 2. So what we're talking about with this is we're actually kind of stretching this out horizontally. And every 2 radians, we'll have another repeat of cotangent. So you can see this is stretching out a little bit further. Remember, in 1 pi radians, we actually have 3.4 radians, okay? So we're going to have every 2 radians is a little bit less than pi radians. So that gets a little confusing, but you'll have plenty of practice problems to go over this with in class, and we'll learn more about how to draw those asymptotes in as well. Finally, we want to talk about damped trigonometric functions. Whenever we multiply a trig function by another function, that causes our trig function to be constrained by that other function, and it's by the absolute value of that other function. And so this non-trig function is called our damping factor. Now, this makes a really fun Desmos investigation, and we'll do a lot more with this in class, but let's talk first about what that looks like. So here we show y equals log of x times sine of x. And this black graph here kind of shows what that does in real life, okay? And I've also graphed log x and negative log x, because you can see that becomes the boundary of our new function log x sine x, okay? So, and this accounts for the absolute value. We're taking the positive and negative version of log x, so log x and negative log x. We graph those, and then in the boundary of that, we're able to graph a regular sine curve. And you can see the sine curve still possesses all the same properties that it would for period and phase shift, because we haven't changed any of that here. So my period is still happening every 2 pi. My amplitude, however, is what gets constrained. See, that amplitude is normally in front of my sine function. Here, instead of that, I have a log x that constrains that amplitude. And because log x is not a constant, okay, we have that acting as a damping factor on our curve. So, as log x gets bigger, in between itself here, the sine x will get a little bit bigger as well, but not much. And you can see this sine must cross here where that log x crosses itself. So all three functions are crossing at that one point. Okay, so it's really kind of an interesting thing to do with Desmos. But suffice it to say, this is just, one of those weird things that we can do with trigonometric functions, and we'll be playing around with it a little bit more in class, but not too terribly much more. So that's it for today. We've learned to sketch tangent, cotangent, secant, and cosecant. We've sketched graphs of damped trigonometric functions, and we'll play around a lot more with these in class and give you some practical experience one-on-one with us, with me learning that. Okay? So that's it for today.